People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Centuries ago, there began something of a curiosity between mathematicians that didn't really amount to much, but some interesting thoughts and some cool mathematical theorems. This form of math had to do with strictly integer quantities, theorems about whole numbers. Things started to change in the 19th century with some breakthroughs in decrypting intelligence through examining the frequency of letters. In the fervor that led to the increase of security of existing avenues of communication and to speed up the newfound media of telegraphy, came a field of mathematics called discrete math. It is now an essential part of our world today, with technologies such as online banking being essentially impossible without it. So what have we learned from discrete math? What are some essential methods used within it? And how is it applied today? All this and more on this episode of Breaking Math. Episode 35, Please Be Discrete. I'm Jonathan.
And I'm Gabriel.
And this is... How do we start the show?
And this is... I don't know. Should we just ask our listeners?
Listeners, if you want us to start the show differently. All right.
Okay.
We're doing an episode on discrete math today, which is a topic. It's one of my favorite topics because I'm a programmer. I have to use it all the time. Any thoughts on discrete math?
Yes, definitely. Actually, as we were talking about doing this topic, the first thought that came to mind is why do discrete math? You mentioned something during the introduction that I think is interesting. You had said that the field of discrete math came out more or less from some curiosities. I'm very curious about more on that, even if there wasn't a practical purpose at the time. What can you tell us from your research about where this field first started, and what were the influences?
Well, it goes all the way back to Euclid and in the Diophantine equations of Diophantes, I think.
I'm less familiar. Who is Diophantes?
Let me look him up. So Diophantus, he was called, apparently, according to Wikipedia, the father of algebra. So Diophantus, he had these equations that were polynomial equations. So you have like x squared plus y squared equals z squared. But if you have x squared plus y squared equals z squared, it usually describes a right triangle, right?
Mm-hmm.
And that right triangle can be any configuration. So if you have like 10, 11, you could figure out the other edge and so forth.
Awesome.
But what's interesting about Diophantine equations is that it restricts it to just Pythagorean triples, which is like 3, 4, 5 triangles, where you have exact integer solutions, which are much harder to solve.
Interesting. The reason why I brought that up is I'm always curious about with the relationship between mathematics and nature and other sciences. We've said this before, that there will be a curious discovery that will have no practical application, and then years down the road it will have an application. So many things fit in that category, and obviously this whole episode is about discrete math, but that's something that fascinates me. So it's almost like curiosity for its own sake, and that only becomes apparent for people like, and I'm sorry, I'm going to slaughter the pronunciation. Say it again.
I think Diophantes or something.
Yeah. Okay, so with respect to discrete math, obviously, we credit him with being the founder of discrete math, but I think the definition is in the term is in the name itself. Discrete math. It's math that focuses on the countable. So that kind of excludes some fields. Obviously, calculus, mathematics of the infinities. I think it's less concerned perhaps with geometry as a whole.
Well, not really. Discrete math and geometry have a huge amount to do with one another. In fact, one of the big discoveries of the last 30 years was Andrew Wiles' discovery of Fermat's last a proof of Fermat's last theorem, which we'll talk about when we talk about more about Diophantine equations later in the episode.
Yeah. Now, obviously, it's huge nowadays because of computing and digital technologies. All of that is nothing but what can be modeled through discrete integers. Ones and zeros. All of that is discrete math. So
yeah, even the real numbers, the way that they're represented in a computer, it uses a finite number of bits, so it's just an approximation to the real numbers. Basically, our whole world right now is digital, and so it's cool that we did some work on this before the digital revolution.
So I'm trying to think of other applications before the digital revolution, before computers, before electric computers that strictly involved discrete math. Like if you go to ancient China, I imagine some of their board games, perhaps.
Well, they did a lot of research in discrete math. In fact, there's this theorem called the Chinese remainder theorem that we're going to be talking about. It was discovered by the Chinese mathematician Sun Zi in some book called Sun Zi Xuanjing. I don't know how to pronounce that.
Again, for those who have a better pronunciation, if you can correct us, we would be very gracious. So why don't we talk about some of the things that we'll be talking about on this particular episode?
Sure, we'll be talking about the Euclidean algorithm for finding the least common denominator of two numbers, which is one of the first algorithms ever to be invented. Then we're going to talk a little bit about Diophantine equations, why they're hard to solve, and the differences between working with integers and real quantities. Mm-hmm. Then we're going to be talking about modulus and the pigeonhole principle, just to kind of show you some of the tools that discrete mathematicians use. Finally, we're going to end with the exponential modulus and how it relates to RSA cryptography.
Very good. Yeah, and I've heard of some of those. In my experience as a math teacher, we did go into modulus. Also, in my limited experiences as a programmer, I know programmers will be much more familiar with the term modulus, but for non-programmers, we look forward to giving a great explanation of what it is, also the applications of a modulus in math involving.
Spoiler alert, it just means remainder.
Indeed.
All right, so Euclidean algorithm is really cool. What do you know about this?
Okay, so let's do a quick Euclid. We've talked about him many, many times. We know that he wrote the Elements, that he is the grandfather. He's basically considered the person who brought mathematical proofs and geometry. He popularized it. He was the first person to create the book Elements that we are aware of. So yes.
No, yeah, he definitely created it.
Okay. Yeah. I'm curious who inspired him. That's always a continuing argument. But he is the founder of 2D geometry as we know it.
And also some theorems about discrete math. One of the cool ones that we could just do real quick is the proof that there's an infinite amount of primes, and this is one of Euclid's proofs.
Fascinating. I'm less familiar with it. No, I've read about it, but I'm less familiar with it.
So basically, let's say you have all the primes, like 2, 3, 5, and let's pretend you had a finite number of primes, right?
Okay.
If you had a finite number of primes, you could multiply them all together, right?
Yes.
And if you did that and then added 1, it would be divisible by none of the numbers.
Oh, that's fascinating.
So it's a new prime.
I love that. That's a very quick proof that you can just explain. I've seen a Facebook group called Mathematical Proofs with Pictures, and hopefully we did a good job of mathematical proofs with just
sound.
With just audio. That's fantastic. So yeah, I'll say it again. So you've got a group of primes. Assume that you have all the primes, and then you said you multiply all of them together, and then add 1. And then that's a new. Is it a new prime or?
Yeah, that would be a new prime because none of the primes so far would be divisible by it.
That is indistinguishable proof of infinite primes.
Because
Cool.
like think about 2, it's not divisible by 2 anymore because now it's odd. It's not divisible by 3 anymore because it's 3 times something plus 1.
Mm-hmm.
So there, etc.
Wow. Now, I assume that that's related to some of Euclid's other ideas. Like I know on our outline here, we've got his algorithm for finding the least common denominator of two numbers.
Yeah, and that one's really cool because it's still used in RSA cryptography today.
Wow. So that term, for those who may not have had a great experience with growing up with math, LCD, that's the last time you probably heard that was in middle school math, perhaps, or pre-algebra. And it's not always fun. It might be a routine task, but it has a lot of applications. As you said, Jonathan, it's for, what was it, what kind of cryptography?
RSA cryptography is one of the steps, one of the many steps. But what's cool about this, I think, is kind of unfair that they don't teach you this algorithm in like elementary school because it's really easy. All you do is you take your 2 prime. So let's say you want to find the least common denominator of let's say 25 and 10.
Okay.
So you divide 25 by 10, and what do you get?
2.5.
Yeah, so 2 remainder 5, right?
Okay. Yes.
So then what you do is you throw away the 25, you put the 10 in the box, and you put the 5 on the outside. So you divide 10 by 5.
Okay. 2.
Remainder 0, right?
Yes.
So therefore 5 is the least common denominator because it was the last thing we divided by.
Oh, cool. So basically it's identifying something as a remainder and then using that as your LCD.
Yeah, it's like so it's like you take the remainder and you keep dividing by the remainder.
Okay.
And you keep dividing what you were dividing by the remainder.
That's fine. You know what? It's just in terms of mental math. So during our first season, we talked a lot about all the episodes that we could do. And in our planning, we even talked about the idea of doing a mental math episode. We never did. It's a fantastic idea. We could actually have people send us emails or letters, hint, hint, or even call us. Do we have a phone number? No, we don't. We are too poor to have a phone number, right?
Oh, yeah, no.
Just kidding. We could have folks contact us any way that they can, breakingmathpodcast@gmail.com, and send us your mental math ideas, things that you may have heard about through the grapevine or, other great mental math techniques. I think that is one way to really garner an appreciation for mathematics and something I wish we all had more of.
Oh, yeah, you could find us too on Twitter @BreakingMathPod.
Yeah. Send us your mental math. We'll do a whole episode on it, and you will get credit. You'll get a shout out.
But yeah, so that's Euclid's contributions to discrete math. Those are all of them. I don't think they were, but let's continue.
So our next section is on Diophantine equations.
Oh yeah, and those are like we talked about them in the introduction a little bit. Things like finding x squared plus y squared equals z squared. Like 3, 4, 5 triangles.
Yeah, I think one of the characteristics of them is that they are harder to find. They are hard equations to solve involving integer quantities. Essentially, that's kind of a description of them.
Yeah, like, and one of the famous ones is Fermat's last theorem. Fermat's last theorem, he came up with it in 1637, and he basically said that if you have x to the n, so x multiplied by itself n times, plus y to the n equals z to the n, it's impossible to solve for n greater than or equal to 3.
That's right. And his last theorem, apparently he proved it in, according to him, he proved it in the margins, or rather, he said he did the proof, but it couldn't fit in the margins of a book. Is that right?
Yeah, we have the quote here, in Latin and in English. Cubum autem in duos cubos, aut quadro quadratum in duos quadro quadratos, et genar liter nullam in infinitum ultra quadratum, potestatum in duos eusdem nominis fas est dividere quius, re demonstrationem mirabilem sane detexi. Hanc marganilis exiguitas non caperet.
It is impossible to separate a cube into two cubes, or a fourth power into two fourth powers, or in general, any power higher than the second into two like powers. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. That is that what we call nowadays as trolling?
I don't think it's trolling. I think he was just kind of full of himself. A lot of mathematicians are.
Now, okay. So, are we saying it's possible that he didn't actually write the proof? Because I mean, a proof that beautiful, you'd think he would have kept track of it.
Oh yeah, definitely. It was probably like he thought he did it, and then he won. And when he went to, I've done this before when I think I solve a homework problem, and then I'm like, go to write it down. It's like, this is not a solution at all. This is just not.
So at one point we talked about doing a show on Facebook called Talking Heads, where we do like little comics of the old mathematicians. We actually talked about doing a Fermat Talking Head, where he do a Twitter where he basically says, "I've discovered a marvelous proof, but the proof will not fit in this tweet," or something like that.
Oh yeah,
that'd be funny.
And his proof, his lack of proof was sustained for 357 years until 1994, not 1991, as I said earlier. It was solved by Andrew Wiles using elliptic curves, which I have only begun to understand.
Oh, wow. What can you tell us about elliptic curves so far, for those of us who have not done any research into them?
Basically, they're equations of the form. I think they're like, it's like x cubed plus x y squared z. I think they're like cubic or less curves, usually set up like polynomials. I'm put on the spot. Like, I barely started looking these up.
Okay, interesting. Yeah, I'd be really curious to dive more into this and hopefully get some more of a grasp of how this proof did it. How big was the proof that finally? How long was Wiles' proof?
It was like 200 pages.
Oh wow! And did he do it all by hand? Did he have the help of a computer?
I think he did. I think it's a by hand proof. I mean, 200 pages is definitely a very long proof. And there's one point where he made a mistake, and he had to redo a chapter and reprove it a different way. So it's always interesting that mathematics can be done like that.
Wow, yeah, that's dramatic. Where you're so close to a solution, and then you have to redo all of it. It's.
Well, he only had to redo one chapter. That was only that was weak.
Wow. Now, one other question then. After he did this, and again, I realize this is as simple as me looking it up, but how soon after he submitted the proof was it accepted?
I'm not sure. I mean, I think 1994 was kind of like the date of acceptance. I think everything is kind of like that, but I don't really know. Wow, I don't know publication standards.
That makes me think that there's certainly a lot of murky things where you have something where you may have a proof, but you don't know yet, and you think that mathematics could potentially be infinitely complex. So just from that angle, there's things that we will never know just because it's in the span of a human lifetime. You'll never get that far.
Oh yeah, for sure.
That's actually, you know what? There's actually a really good blog. We've talked about it before. It's the Star Codex. What was it called again?
Oh, I don't remember exactly.
I will find out real quick. Star Slate Codex. There's a blog on the very popular Star Slate Codex that is all about the absolute limits of human knowledge, and it's a fantastic blog. They talk about people who spend their entire life researching, and then you've got other people who spend their entire life teaching people to research, so that they can hopefully do it better. And there's only so many improvements that you can make, that there's this asymptotic limit, it seems, to human knowledge. It's a really great read. If you haven't had a chance, I would suggest go check out Star Slate or Slate Star Codex.
So one of the tools that you use a lot in discrete math is modulus, which is just remainder. So 7 modulus 3 would be what?
Oh, okay. So 1, right? Because
Yeah, and the way that you could say that is 7 is equivalent to 1 modulo 3. And I don't know why that's the notation, but that's what everybody settled on, and it really annoys me. I think it should just be like in computer programming, you usually use a percent sign. And to me, that makes more sense to keep it as an operator, but that's just my own personal politics.
so that's what immodulus does. And I know that this became a thing, as you said earlier, with ancient Greek mathematicians.
Oh, ancient Chinese too.
Oh, really?
Yeah, there's this thing that you could actually do with modulus called the Chinese remainder theorem.
Okay.
And so let's say I give you a certain number of coins, and you have a jar that each holds a certain number. Like, let's say each jar holds 3 coins, and you put.
What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
These coins into these jars, and you have 2 coins left over.
Okay.
Now you do another one, but with the coins where the jars hold 5 coins, and you have 3 left over. And if you do it with 7, then you have 2 left over. And with the Chinese remainder theorem, it is possible to reconstruct the original number, which is 23 different coins.
Oh, okay. Interesting. Wow. This is fascinating. So I'm actually very curious. This is an area, again, this is probably more history than it is math, but you certainly inspired me to suddenly research parallel developments in ancient China and other parts of the world.
I think China was kind of unparalleled in number theory.
Unparalleled, huh?
Yeah, the Chinese and the ancient Indian mathematicians were really good at that.
Fascinating. So what's older, the mathematics that you're quoting, or the mathematics of Euclid?
I think Euclid was a little earlier.
Okay. And then obviously with respect to one culture influencing the other, a lot of the things that were in China, India, and Greece were fairly independent. Is that right?
I'm not sure. I think there's a lot of debate about how much cross-pollination there was through trade.
Yeah. I also know that there's a lot of things that are ascribed to things like Archimedes that were actually could be described possibly as ancient Egyptian. Again, I'm not an expert in this area, so I could be completely wrong on this one. But it is an interesting topic to talk about the actual origins of things, or it could be like where Rome conquered ancient Greece and just took their ideas and renamed them. So.
Oh yeah, and there's also there's a lot of factors. But what's cool about the Chinese remainder theorem is that it's used to this day in RSA cryptography. It's used to solve a problem which we'll be talking about in a second, where let's say actually we could just do this now. Let's say I wanted you to multiply 9 by itself 100 times, so 9 to the 100th power.
Yes.
And tell me the last digit of that real quick.
Oh, wow. Okay. I've got no idea. I mean, I have to, 9's a funky number. It's one of my favorite numbers.
Well, here's the thing to notice.
Yes.
9 to the 100th is 9 squared to the 50th, right?
Yes.
9 squared is 81.
Okay.
The last digit of 81 is, the last digit of any number is that number modulo 10. You divide by 10 and take the remainder.
Oh, wow.
So, and the cool thing about modulo is that like 12 times 13 is going to be 6 modulo 10, because 12 is 2 and 13 is 3. Okay. So you can multiply with modulo. You could do a lot of like arithmetic with modulo. You could add and subtract. You just have to keep track of it on both sides.
Wow. So essentially what you're saying is this comes down to a mathematical do-si-do.
Basically.
Like it's a barnyard dance, but with numbers, and you end up with grab your partner, swing around, and you end up with the last number.
Yeah, definitely. And that's actually a pretty good analogy because 9 squared is 81, so the last digit is 1. And what's 1 multiplied by itself 50 times?
1.
Yeah, so the last digit of 9 to the 100th is 1.
Oh, wow. Okay. Odd man out. Interesting. Okay. Very cool. Very cool.
And you could do the same thing with with a lot of numbers, and that's actually why I want you to solve this at home. If you have a number and you add up the digits and you keep adding up the digits until you have one digit left, if that digit is divisible by 3, then the original number was too, and you can figure that out using modulo.
Fascinating. Wow. That's right. We are now assigning our Breaking Math listeners math homework. Just kidding.
Yes.
No, we're not going to. Boy.
It's required to listen.
Yes. You can't listen to Breaking Math unless you do the math homework.
In future episodes, we're going to have to submit it by email. We're going to have to grade it. If you get an A, you get to listen to the whole episode.
I'm sorry, guys.
If you get a B, you can listen to 45 minutes. If you get a C, you get half an hour.
You don't get the... Oh, gosh, dude. We're going to lose our listeners so fast. Because I think at business practice, the worst thing to do is to tell someone what they have to do. So
grade your customers.
Yes. Oh boy, that's not a great business practice here. So are you going to keep that in, or are you going to edit that out?
No.
Oh man. Okay. Yeah. Now the whole idea that I said earlier is I was trying to imagine this whole modulus do-si-do thing. This brings me back to our episode on Math Factory. We were talking about our favorite algorithms in general. Essentially, that's what it is. Like you've got a problem to solve, and you've got all these different algorithms. It's basically are kind of a song and a dance where you end up with something, and that's the brilliance of mathematics, and that's the brilliance of algorithms. So
yeah, and sometimes I feel like it does have the same feeling as dancing, at least certain types of dancing, like definitely the do-si-do type of dancing, because it's about steps.
Yeah.
You have quantized steps in discrete math versus like infinitesimal calculus is a different story.
Yeah. You've got like you talk about like things that are understandable with respect to information theory. Well, there's a pattern, and what you just described, that do-si-do with mathematical systems, that's it's very easy to describe how it works, and it always produces an end result. So it's exactly like a dance. It's cool. That's cool.
Yeah, and the cool thing about like modulo is the way that I visualize it in my head is a ring of beads. So like if 100 modulo 7 is just you have a ring with 7 beads on it, and you just go around it until you pass 100 beads.
Perfect example of discrete math, using beads as counting. In fact, that all brings you back to math, how it began with calendars and counting and all that stuff.
Yeah, it's very like earthy math in my opinion.
It's like you can't get away from math, man. No matter what you do, you could try to run away and get away from it all, but you never ever will.
Math always finds you.
And sometimes you find math, or math finds you. Like that. That's mystical math. That'd be a good episode, wouldn't it?
Yeah, it would. But we could do Tesla.
Okay.
But one cool thing about the exponential modulus is that it's used in RSA cryptography, and the way it's calculated is actually we can't go into it because it's really complicated. Well, not really complicated, but we don't have time to really go into it. But it's used in it uses the Chinese remainder theorem, but you could use exponential modulus the same way. And so, let's say I have something that I encrypted with my public key. That's to say, if I have a public key, just a quick rundown of that. I could use it anybody can use it to encrypt messages, but only I can use my private key to decrypt them, right?
Yes.
So usually you have a ciphertext. To make ciphertext in RSA, you take the message, you take it to the exponent of the public key, which is usually a few hundred bits, and then you divide that, and then you take that modulo n. Yeah. And n is just a pre-agreed upon number.
So there's a lot of terminology here, and I understand that our audience, our listeners right now who have computer science and math backgrounds, they're probably following right along. But for those who are listening in the background who may not have any background whatsoever, let's how would we say just what you said using just pure analogies? I think one possible way of doing it. You mentioned cipher. A cipher is a way of decoding something. Yeah.
Yeah, and also okay, so what's when you multiply something by itself modulo n, essentially what you're doing is you're just kind of scrambling the number over and over again.
Okay.
It's kind of a way of scrambling the number, and you could actually create some really cool diagrams with this.
If you had some information, an order of something, you could scramble it I'm trying to think of some example involving like baskets or like a lottery spinner or something. You know what I mean? Yeah,
it's kind of like that, but where it's predictable every single time.
Okay.
And so anyway, you just scramble it by multiplying it by itself. Like if you followed the algorithm to the letter, you'd have to keep doing this for like almost for literally more time than the universe has existed, multiplying it by itself over and over and over again. Because these digits are like hundreds of like binary digits long. These are gigantic numbers that we're dealing with, but there's a trick, is that we multiply it by itself over and over again. And like the reason why this is fast is 2 times 2 is 4 times 2 is what?
8
times 2 is
16
times 2 is
32.
So in 5 steps we got to 32. But 2 squared is
4
squared is
16.
16 squared is
256.
and 256 squared is a very big number. And in 5 steps we've gotten to like a way big number. And so that's why the squaring trick works. We just square and multiply it by itself.
Real quick question. This is something I should have asked you earlier. You said the name of this encryption is it's R. I'm sorry. What is it?
RSA.
RSA. What does RSA stand for?
It stands for the 3 inventors of the algorithm: Ron Rivest, Avi Shamir, and Leonard Adelman.
Okay. And when did they come up with this way of doing it?
1978. There's an equivalent system that was developed in 1973 by an English mathematician, but it wasn't RSA, but that wasn't declassified until 1997.
Interesting. Okay. And then, wow. Okay. Huh.
And so these require like 4 kilobits of information to basically scramble everything up. And so when you take your message, raise it to the exponent of the public key, and take it modulo n, you're just scrambling up that information.
Mm-hmm.
But what's cool is that to descramble it, you use the same algorithm, but the exponent is even bigger. It's your private key.
Interesting. Okay. Public key, private key. And I'm trying to think of like what are some other analogies for the whole public key, private key thing?
Like a mailbox, or like a good way to think of it is like, let's say I want you to send me a something secure.
Mm-hmm.
So I give you a box that is pre-locked that you put messages in.
Mm-hmm.
That's like encrypting it with my public key.
Cool.
And then when the box gets back to me, I have my key in my pocket, and that's opening it up with my private key.
Got it. Okay.
One of the last things I think we're going to talk about is the pigeonhole principle. And it's a really simple principle, and it's like if you have more pigeons than you have pigeonholes, then there's at least one pigeonhole with more than one pigeon. And that's how simple it is.
Oh, yeah. Sorry, I was visualizing that for me. Yeah, because it's a remainder problem. You got to stick 2 pigeons at least 2 in at least one of the holes.
And there's an extended pigeonhole principle, which says that if you have like 3 times as many pigeons as pigeonholes, then there's at least one pigeonhole with at least 3 pigeons.
Oh, wow, that's interesting. Yeah, it's one of those things where I feel like I'd have to count it out to start to convince me of that.
Yeah, or at least 4. I mean, and the reason why is because, like, let's say you have like 10 pigeons and 3 pigeonholes.
Mm-hmm.
You could put 3 pigeons in each hole, and then you have 1 left over. So you have to have 1 pigeonhole with at least 4 pigeons.
Oh, okay, got it.
And it still holds if you have 1 pigeon in pigeonhole 1, 1 pigeon in pigeonhole 2, and then 8 pigeons in pigeonhole 3, because that's at least 3 and at least 1.
Mm-hmm. Interesting.
And it's cool because you could use this to prove that there's at least 2 people in England with the exact same number of hairs on their head. And the way that you could do that is this. So there's about 1 million, and this is a fact, there's about 1 million, or no more than like 1 million hairs on a head, even like generously, whatever.
Okay.
Which means that there's about 1 million pigeonholes, the people with 1 hair on their head, 2 hairs on their head, all the way to 1 million hairs on their head.
Okay.
And if there's more than 1 million people in England, which it's true, it means that there's at least 2 people with the same number of hairs on their head.
Oh, got it.
In fact, because let me see how many people are in England.
Oh, that's crazy. That's so simple. It's deceptive, dude. Deceptive mathematics. How about a whole podcast called that?
And there's about 66 million people in England, which means that there's at least 67 people walking around with the same number of hairs on their head.
That's extremely convincing. Fascinating.
And it relates to the birthday paradox too, and this shows the difference between probability and pigeonhole principle. Because if you have 23 people in a room, as we've covered, I think, on the podcast before, there's at least a 50% chance that 2 people will have the same birthday.
That's crazy. So in this case, if we talk about this in terms of the pigeonhole principle, of course there are, if you're not counting leap year, there's 365.25, whatever, days in a year.
Let's just round to 365.
Okay. So yeah, for the sake of this discussion, then we'll just say 365. But we're not using the days of the year as pigeonholes, right?
Yeah, we are.
Okay.
And which means that even though there's a 50% chance with 23, for there to be a 100% chance that two people have the same birthday, you have to have at least 366 people.
Okay. Interesting. Okay. Wow. And then what was the logic of that one again? Like, how do you prove? So 100% chance you have to have the exact amount of pigeonholes.
Or you have to have at least as many.
Okay.
Because there's only a certain amount of birthdays. So at some point you're going to have to start repeating birthdays.
Mm-hmm.
So if there's 366 people in a room, there's a 100% chance that two of them have the same birthday.
And if you want a description of why that's not the case, or rather why it's unintuitive that you only need, what was it, 23?
23 for 50%.
Yeah, we answered that in a previous episode. I think it was minisode 6, I believe.
I think so. Yeah, you could go back and listen to that.
Mm-hmm. That's a great discussion. Very unintuitive. Are there any more applications of the pigeonhole principle? Because I mean, like we did some of them, but like
I mean, there's like, it's just used all the time in like little proofs. It's a tool, you know. It's a tool to be used all the time, and it's just useful because like let's say you have people shaking hands together.
Mm-hmm.
You could prove that at least two people shook the same number of hands. Using the number of handshakes as pigeonholes. So it's like if you make more abstract pigeonholes, then you can prove cooler things.
Okay, very cool.
Discrete mathematics has shaped the way in which we relate to the world through the process of not only digitization, but encryption through digitization. As we continue on to the sister episode to this one, which will be about mental and recreational mathematics, let us remember that our world today is defined by sharp definitions in between numbers. I'm Jonathan.
And I'm Gabriel.
And this has been Breaking Math. If you want a poster, where can you get that?
Oh, if you go to our Patreon, and that is www.patreon.com/breakingmath. Not Breaking Math Podcast, just Breaking Math.
Yeah, and you can find us on Twitter at Breaking Math Pod. You can find us on Gmail at Breaking Math Podcast. And yeah, I think that's all I have.
Yeah, I have a few things. First, I want to say the posters are now shipping much, much faster. We were, with the revenues from our original, not to get too into details, but with the revenues from the first posters, we were able to finally order a medium-sized bulk order. So we've got a whole bunch of them. So this is right in time for Christmas. So until we run out of this amount, which is, I think it's 4 times our original order.
Yeah.
Okay, we're hoping that this. I'm sure it'll last, but they're shipping much faster now. So from the day you order it, it's assuming that the day you order it is the day that I go down to the UPS store and mail it. In the United States, it's arriving in probably 3 or 4 days. That's it.
Yep.
So, yeah, and aside from that, we mentioned earlier, please send us your favorite mental math. We love talking about it. That's great discussion. That gets us excited. And if you want to send us your favorite mental math or your favorite recreational math, we will make sure to include it. Well, I can't say that for sure. It's a guarantee that I can't hold to.
We'll think about including
We'll
it.
think about it.
If you're not terrible.
Oh, gosh. Yeah, please send us your stuff. Talk to us about your favorite math games and your favorite mental math. It'll be a great discussion next time.
And I know we joked about it earlier in the episode, but we actually are going to move to a grading-based subscription format.
Oh, good Lord. Yeah. Oh, and lastly, if you guys want to follow me, I'm actually going to start making YouTube videos that reflect on podcasting in general. I've been listening a lot to almost everything from Gimlet Studios. They're an inspiration in terms of how they created the company. Not everything that they've done has been well received by the audience, but I've been obsessed by Gimlet, especially the podcast Startup. I'm just plugging it because I am. I'm going to start making Facebook videos that I release where I talk about my favorite podcast as well as what I want to do with Breaking Math. So if you'd like to, feel free to friend me on Facebook. Just go to Gabriel Hesch and you'll see a few of those. That's also another way to interact with me. So yeah,